Hi everyone, how's it going? We're going to move on to the next section. The book title is actually Integration of Rational Functions by Partial Fractions, but it was too long, so I just contracted it to this. But the name says it all. There's two things that we want to think about. Is what was a rational function again? Step one is, what were rational functions? Well, these were functions of the form we'll just call it capital R of x for rational, p of x divided by q of x. So they are the division of two functions, but these two functions are very specific types of functions. These are both polynomials. So rational functions are functions that take one polynomial and divide them by another. And then remember, polynomials were just functions in this form. This is the technical way of writing it. But this just means it's a function that has different powers of x. So x squared, x cubed, x to the fourth, x to the 0th, which is just 1, along with these coefficients. So examples of these are, 3x squared plus 4, 17x to the fourth minus 7x squared. These are just functions in the following form. So they have some coefficients. So like technically, this would be a2, and then this would be a sub 0. This would be a4, and this -7 would be a2 in this case. So they're just coefficients in front of x to some power, and you add or subtract these terms together. And now remember what the degree of a polynomial was. The degree of a polynomial which we'll write deg of p, or whatever polynomial we stick in there. So this letter could be q, x, y, z, but we'll just call it p. So the degree of a polynomial p, which we'll write deg of p, parentheses p, is the highest power. So it's the highest power of the polynomial function p of x. So for example, the highest power I see here is a 2, so the degree here is equal to 2. And then the degree here, I see the highest power is 4, this is going to be 4. Okay. So rational functions are one polynomial divided by another, and we want to keep in mind what the degree of a polynomial is. It's just the highest power. Okay? So then, we're interested in taking the integral of these types of functions. And now there is no quotient rule necessarily or anything like that for integrals. And so we need to develop a technique to deal with this division of polynomials. And this technique is called partial fraction decomposition. So the technique is partial fraction decomposition. So the goal of partial fraction decomposition is to take a rational function and write it as the sum of more easily digestible or more easily integrable, in this case, functions whose integral we can take. So let me just give you an example. Say we have the following rational function. Then we'll learn how to do this in a second, but the technique of partial fraction decomposition will allow us to break this complicated rational function, notice this is one polynomial over another, into two more easily integrable rational functions. So notice we broke this up. So this more complicated thing, whose integral I don't know how to take, breaks up into these two things, and I do know how to take each of these integrals. And that is the key to this. That's why we do this partial fraction decomposition. And so these pieces here, they're known as the partial fractions of this original, rational function. So we're decomposing the rational function into partial fractions who, if they combine together, will give back the original rational function. But we don't want to combine them, we want to break it. So we decompose this rational function into the smaller pieces. Okay? And now the thing is, this can always, in a sense, I don't want to say always, but many times can happen under certain circumstances, in particular if we have this rational function we'll see that in this scenario, so the degree of the top is less than the degree of the bottom. So maybe this has the highest power is 3, the highest power here is 5. Then we can do this decomposition. In general, sometimes it'll be a little harder, but in the case of this class, in this context, we'll be able to do it. So we'll be able to do this decomposition. Okay, so let's actually look at the original problem that we had and see that it does satisfy this. So the original integral that we were trying to do was this. This guy here. And so now what we want to do is we just want to completely ignore the integral for now and just look at algebra. How can we rewrite this? And our desire, our goal, first off, is to turn the bottom into, if we can, we want to factor the bottom. And notice that the degree of the bottom is 2 and the degree of the top is 1. Therefore, we're in that scenario where the decomposition is possible. So step 1 is let's factor the bottom into x minus 2 and x plus 1. Or sorry, plus 2 and minus 1. There we go. Okay, so now that we factored this guy, this is the key here, is if you factor the bottom completely into, these are called linear terms. Why are they linear? Well, these are the equations of lines, right? This is in the form y equals mx plus b. This is in the form y equals mx plus b. They both have m is 1, but their b is different. So these are called linear factors because they give you, a linear equation. So a linear factor is just something in the form ax plus b. So here a is 1, b is 2, here a is 1, b is negative 1. So if we do have this thing broken down into linear factors, what we're going to do is we want to be able to split this fraction up into something like this. Some constant a over one of the linear factors plus another constant b over the other linear factor. Our goal is to do this. We hope that this can be done. Because if this can be done, we can take these integrals. And I'll talk about why in a second. And so if these things are all equal, the integral of this is equal to the integral of that. And this we can do, but this we didn't know how to do. So now if we forget about the middle, this step for a second, and just look at these guys, what I'm going to do now is I'm going to multiply both sides by this guy here, by x plus 2 times x minus 1. So it cancels out over here. And then this has to hit each term on this side, or x minus 1. Okay? So cancels out here. So now I'm left just with x plus 5 equals, so when this x plus 2 hits that x plus 2, it cancels, but the x minus 1 lives. So I have an a times x minus 1, and similarly I'll have a b times x plus 2, because the x minus 1 cancels here, and the x plus 2 lives. Okay, and now my goal is to find a and b. If I can find a and b, I'm in business. So there's a lot of tricks that you can do. One of my favorite ones is to just let x be different values so that it kills off one of the terms. So let x be 1. So if x is 1, what does this equation turn into? It turns into 1 plus 5, which is 6. And then it turns into a times 1 minus 1, but this is the great because this is 0. So it kills this term, and then we're just left with b times 1 plus 2, which is b times 3, or 3b. And why is this so nice? Well, I immediately know what b is now. B is 2. That's the beauty of this trick. And now we're going to do something similar. Now we'll let x be negative 2. So now if you let x be negative 2, we get negative 2 plus 5 is 3. Then we get a times negative 2 minus 1 plus b times negative 2 plus 2. Well, notice this goes to 0. That's perfect. And so then we get negative 2 minus 1 is negative 3 times a is negative 3a. And so this tells me that a is negative 1. And now we know a and b. This is perfect. So what we know now is that the thing that we started with, x plus 5 all over x squared plus x minus 2, was equal to the original, to when we factored this, x plus 5 times x plus 2, x minus 1. And now this is equal to, this is awesome, I know my a and my b now. So negative 1 over x plus 2 plus 2 over x minus 1. That's what a and b were, so I just made that substitution. And this is what we saw earlier. And the beauty of this now is that if I take the integral of this, it's the same as the integral of that. So the integral since they're equal, right, is the integral of just this and then this integral we can just look at each separate part. So we break this up into the sum of two different integrals. And now you may be thinking, well, we don't know how to take these integrals. Yes, we do. With one quick u substitution, this becomes an integral that we're very familiar with. So if we let u be equal to x plus 2 here, du is just dx. And this will always happen with these linear factors is, you know, if there was like a 3 here, you'd get a 3 or something. So you may pick up a constant, but the nice thing is you'll just get a constant times dx. In this case, it's just 1. So either du will be dx or du divided by some constant is dx. This is the beauty of this. And then same thing here. If u is x minus 1, du is dx. And so these integrals become much easier to deal with because now they transform into -1 over u du plus 2 over u du. And we can do these all day long. 1 over u is the ln of the absolute value of u. So we get negative ln absolute value of u. And then this one is just 2 times the ln of absolute value of u. Because this 2, you could have floated it out in front. And the integral of 1 over u is ln absolute value of u. And so now what we know, after all this work, is that the original integral that we started with is actually just negative ln of the absolute value. And let's substitute back for what u was. In one case, u was x minus 1. For this one it was x plus 2. So we get negative ln of x plus absolute value of x plus 2, and then plus 2 times the ln of the absolute value of x minus 1. Yeah, sorry, I erased it. I should have kept it. But how did I erase it? You know what to substitute back. And then plus c. And there we go. That's the value of this integral. So the partial fraction decomposition allowed us to do this. It was very cool. And this technique is used a lot. So it's not just a one time and done deal. It's pretty frequently seen. Okay, so that's cool. Now you may be wondering what happens if we don't have that very special scenario where the degree of the bottom is larger than the degree of the top. When this happens, we need to do long division in order to reduce the power of the top and then leave it in a more nice format. So let me just do an example and you'll see what I'm talking about. So let's say you want to find this integral. So notice the degree here is 3, the degree here is 1. So we're not in that scenario that we were talking about. So step 1 is actually you need to do polynomial long division. And it's probably been a while since you did this. So we're going to take x minus 1. So we're taking this guy divided by x minus 1. So we, write it in the standard way that we write division. And then, so what did you do in polynomial long division? So what you do is you take this term here, x cubed, and then you divide it by this term, x. And then you're left with an x squared. So when you do that, you're left with an x squared. And then what you do with this x squared is you distribute it to this term here. So you distribute it to that. So x squared times x minus 1 is going to be x cubed minus x squared. And then what you do with this is you take this original polynomial and subtract this from it. So if you're subtracting this, that means that you tack on a minus sign out in front, and this will essentially just flip the sign on all of these. So now we'll write that. So negative x cubed plus x squared. And now you just want to add these things up. So when you do that, x cubed minus x cubed is 0. And then you're just left with the x plus x squared. So then you're left with x squared plus x. All right, you just add these now. Because we already took into account the negative sign. Okay, so now you add these, and this is what you're left with. So x cubed plus x, so let me do it all in one line. So we took x cubed plus x minus x cubed plus x squared. That's literally what we did. These canceled, and then we're just left with that. Now, again, what you're going to do is, until the degree of this remaining polynomial is less than the degree of this, you're going to continue the process where you take the x squared and now you divide that by x. So when you do that, x squared divided by x gives you x, so we say plus x here. And then you do the same thing. You take that x and you distribute it to x minus 1. And then you take this and you subtract it from this guy. So we're essentially going to take x squared plus x minus this quantity, this entire quantity. So that's essentially, you know, if I make this negative, so I tack on that minus sign again, this is negative x squared plus x. So I'll put a negative x squared and then plus x here. So then when you add those, you're just left with 2x. And then because this is x and that's x and they have the same power, you can do this again one more time. So now you take x divided by x, and that just gives you 1. And now distribute that 1. Well, that just gives you this back. And now subtract this. So subtract. So we're going to take 2x minus x minus 1. And that essentially makes this 2x minus x plus 1. Let me see. Oh, I'm so sorry. I did x divided by x, but it should be 2x divided by x. So this should actually be a 2. So sorry about that. So that should be a 2. So this is 2x minus 2. Okay. So then when we tack on the minus sign in front of that, this becomes negative 2x plus 2. So we have negative 2x plus 2, and what remains is a 2 when you add those. Okay. Now this thing has degree 1, and the degree of a constant is 0, because technically this is 2 times x to the 0. So this has degree 0. So we can't do this anymore. Once this thing has degree less than this guy, you have to stop. So now this is just like regular division. This was the quotient, and this is the remainder. So we know that we can rewrite the division as the quotient plus the remainder divided by the thing we were dividing by. So this. Okay, that's pretty neat. And now look at this, all the work has been done. We can take the integral of all of this now. So the integral of the original thing the integral of this is the same as the integral of that. And then we could do all of these now. So the integral of x squared is 1/3 x cubed. The integral of x is 1/2 x squared. The integral of 2 is 2x. And then using that same u substitution trick, if we let u be x minus 1, notice that du is again dx. So the integral that we're left with is the integral of 2 over u du, which we know how to do that. So this becomes 1/3 x cubed plus 1/2 x squared plus 2x plus 2 ln absolute value of u, but what was u is x minus 1. And that's our answer. So this is equal to the integral that we started with. Very cool, right? This trick is quite amazing. Okay, so very nice. Probably haven't done long division in a while. I definitely haven't done it in a while either, so I had to think about it for a second. Okay. And now let's do another example, but here it's going to be slightly more complicated, but the same idea applies. So now we're going to take the integral of x minus 2. So we have this. So step one is we have to think about, is the degree of the bottom larger than the degree of the top? And the answer is yes. This has degree 3, that's 2, so we're good. We don't have to do any long division. And the next step is, remember, and let's ignore the integral now, let's just do algebra. The goal is to factor the top and the bottom as much as possible. Now the top does not factor. With real numbers, you cannot do this, because the only combination that gives minus 1 is plus 1 and minus 1, but that would cancel out, and that cannot give you the 2x. So the top doesn't break down at all. But in the bottom, notice there's a common factor of x, so we can pull that out. And then with the remaining thing here, we can factor this even more. So I need a 2x and an x to give me 2x squared. And now if I make this a plus 2 and a minus 1, this will work out, because this will give me 2x squared plus 4x minus x. That gives me the 3x and then minus 2 here. Okay, so now we've broken this down into 3 linear factors. One is x, one is 2x minus 1, and the other is x plus 2. And this is the exact form we want it. We want to break down these things as much as possible. So in this case, the best case scenario is all linear factors, which we do have. And now again, we do the same trick. We would like to write each of these. We would like to break this down into something like this. Decompose it into this guy. And so we're going to do the same trick we did last time. Is what we'll do is we'll multiply both sides by the denominator here. And so we'll multiply all of this Sorry, there's no room here. So multiply both sides by that. So here it cancels out. And that's good, we wanted that. So now we have just x squared plus 2x minus 1 equals, okay, so when this x hits that x down here, it cancels, but the other two factors will remain. So this will be a times 2x minus 1, x plus 2. And then same thing, the 2x minus 1 cancels, but the other two factors live. So this is bx times x plus 2, and similarly, we'll have cx times 2x minus 1. This is what happens when we do this. Okay, and now we're going to play that same game that we did at the beginning. So notice, if I let x be 0, that'll kill this thing, because b times 0 is 0, and then 0 times anything is 0. And same thing here. So that's exactly what I want to do. Because this doesn't have x here, that's perfect. This will live. So let x be 0. What does that tell me? So you get 0 squared plus 2 times 0, which is 0 minus 1. So you'll get negative 1 equals a times 2 times 0 minus 1, 0 plus 2. And this is what I was talking about. This will be b times 0, but b times 0 is 0, times 2 is 0. So that's dead. And for the same reason, that's gone too. And that's perfect, because now I have a isolated. So this tells me that negative 1 is, so 2 times 0 is 0, minus 1 is negative 1. So I have a times negative 1 times 2, better known as negative 2. So I have negative 2a, which tells me that a is positive 1/2. So I'll take a note of that up here. A is positive 1/2. Okay, sweet. So I know that. And so at this point I can replace this with 1/2. But I'm just going to keep pushing this trick as far as I can without needing to invoke the fact that this is 1/2. So the next number I'd like to plug in is negative 2. Or I guess if you want to go in order, I'll plug in 1/2. So see, if you plug in 1/2 here, you'll get 2 times 1/2, which is 1, minus 1. This is 0, so it kills all of that. Now this doesn't have the 2x minus 1, so it won't go away, but this will also go away. So if we let x be 1/2, now what do we get? And you may be wondering, why does this trick work? Well, this equation is true for every value of x. You know, this has to be true for all values of x. This is what we desire. That's what it means for this to be equal to that. For any value of x I plug in here, this should work. And so if this is true, letting x be a particular value, this equation should still hold. So that's why this trick works. So, okay, if you plug in 1/2, you'll get 1/2 squared plus 2 times 1/2 minus 1. Okay, so 2 times 1/2 is 1, minus 1 is 0, so that's dead. And then 1/2 squared is a fourth. So we have 1/4. And then like I was saying, this becomes a times 2 times 1/2 minus 1 times 1/2 plus 2. But notice that this is 1 minus 1, which is 0. So we have a times 0 times 5 halves, but it doesn't matter. The 0 multiplies, and it takes away this entire term. And the same thing happens here. So all we're really left with is b times 1/2 times 1/2 plus 2. Okay. And then now this tells me that 1/4 is equal to, so b times 1/2 times 1/2 plus 2 is the same as 1/2 plus 4 halves, right? This is the same as 2, which combines to give me 5 halves. And so when you multiply these, we get 1/4 is equal to 5/4 b. And now multiply both sides by 4. 4/5, I'm sorry, so multiply both sides by 4/5. that kills this guy here, and then when this cancels, we get 1/5. So b is 1/5. So we know that. And then last but not least, if I want to get rid of this term and that term to get c, I'll let x be -2, because that'll kill these guys off. So then, let x be equal to -2, and then we get -2 squared plus 2 times -2, which is 4 minus 4, so that dies, so that's 0. And then we're just left with that -1. So -1, and then these two terms will be killed off when x is -2. So I'm really left with is c times -2, 2 times -2 minus 1. So what does this tell me? This tells me that -1 is, so 2 times -2 is -4, -1 is a -5 overall, so this is a -5. So -2 times -5 is +10, so I have -1 equals 10c, which means that c is -1/10. Beautiful. Now I have all of my coefficients. So now that I have all of my coefficients, I'm in business. Because I know a, b, and c. So I know now that my original integral which we, did some manipulation and broke it down, the bottom into linear factors. Regardless, we know that this thing equals that. So this is the same as the integral of a, which is 1/2 over x, plus b, which is 1/5 over 2x minus 1, minus 1/10 all over x plus 2. This is so cool. I mean, look at that. I mean, who would have thought? And so now we can do each of these three integrals separately. So in the first integral, 1/2 over x, you can just pull the 1/2 out in front, and this is like a 1, our favorite integral here. And then the same thing, you can pull that 1/5 out, and you have this guy. And then pull out the 1/10, and you have that. Okay, so then now, going up here, this becomes 1/2 ln absolute value of x, plus, okay, now this one you can do with a quick u substitution. And after a while, I think you'll catch the trend, you won't need to keep doing it. If you let u be 2x minus 1, that means that du is just 2 dx, right? And so du over 2 is dx. So that's the price you pay. So this integral now becomes 1/5 integral of 1 over u du over 2, but pulling out this 1/2 just turns this into a 1/10, and then we're just left with that. And now again, technically, because I used u, I shouldn't use u again, but if you're just conscious about what you're doing, it's fine. But let's just pick another one like m. So let's let m be equal to x plus 2. Then we see that dm is dx. So that one comes with no charge. So then this becomes minus 1/10 integral of 1 over m dm. And so we now have 1/2 ln absolute value of x plus 1/10 ln absolute value of u, which u was 2x minus 1, minus 1/10 ln absolute value of m, but that is just x plus 2, and then plus c. And that's the value of our integral. You can do, you can use some of the log rules here to make this a little simpler, but we'll just leave it like that. We won't sweat about the details too much. Okay, and so yeah, from now on, probably with these types of u substitutions, I will omit the explicit calculation just for time's sake, so we'll just do it in our head. Okay. Okay, so now the next scenario is, what happens if we have linear factors, but it's a repeated linear factor? So that linear factor shows up more than once. So let's see an example of this. So let's do the integral of x to the fourth, not much better, x to the fourth minus 2x squared. This one's actually quite faint. Plus 4x plus 1 all over x cubed minus x cubed minus x squared minus x plus 1. Okay, so now again, the first step that we had to make sure was, is the degree of the top less than the degree of the bottom? In this case, it is not. The degree of the top is 4, and the degree of the bottom is 3. So we have to do long division first as a preliminary step. So if we do this long division, and then I'll do this a little quicker. Than the first time. Just making sure everything's right. Yes. So we take the x to the fourth divided by x cubed. That gives me an x, and that x distributes to all of these. So I get x to the fourth minus x cubed minus x squared plus x. And then I take this minus that, meaning I flip the sign on everything and now combine. So these cancel. This leaves me with a negative x cubed. Oh, I'm sorry. This negative 2x, so the x cubed doesn't combine with anything. Negative 2x squared plus x squared gives me a minus x squared. And then 4x minus x is 3x, and then plus 1. And then we do this again, so we take x cubed divided by x cubed, that gives me plus 1. Now 1 times this just gives itself. And then flip the sign on everything, so minus, plus, plus, minus, and combine. These cancel, and you're left with now just a 4x, because these also cancel. And because this has degree 1 and this has degree 3, we have to stop. So, we now know that we can break this down into, you know, the quotient plus the remainder over the divisor. So this guy. Okay. And then we know how to take the integral of these two, so that's good. So we want to focus our eyes now on this. Because now the degree here is 1, that's 3, that's good. We can do the partial fractions. So let me just keep a mental note of this up here. And so we can just focus on this. Okay. So now we just want to focus on the second piece. Okay, so again, the idea was to factor the bottom completely. The top is already factored. It's not going to get more simpler. So then the bottom, let's think about how we can get the bottom. Maybe we'll need 3 pieces here to do this. So then, beforehand though, we always want to start with just 2 pieces. So let's say we have this guy times that. Okay, so if I want an x squared here, then this has to be an x, right? To give me an x cubed. And then the next thing is this is a plus 1. The only way to get a plus 1 is plus 1 plus 1, or minus 1 and minus 1. Because there's minuses here, I think it's better to do minuses. Okay, now let's see if this works out. So x squared times x is x cubed, minus x squared minus x plus 1. Beautiful, so it does work out. And this is not fully factored yet because this factors into the following. X minus 1, or let me write it like this. X plus 1 times x minus 1. This factors into that. And then times the x minus 1 remaining. So, actually these two combine. And this is what I mean by a repeated linear factor. So we get this. So the fact that there's a squared here means there's 2 x minus 1s. And so this is the form that we're going to want to look at, because this is the one where it's completely factored. So now we're going to do the same trick. We're going to write this guy but now there's a catch. Because this thing shows up twice, this is how we take care of it. We'll have 1a over x minus 1, and then another one will be x minus 1 squared. You know, and then had this been a cubed, you need a plus c over x minus 1 cubed. So you kind of catch the drift. So you have to do this up to however many powers of this there are. And then there's only 1 power of this, so we can stop here with that. Okay, so that's the only catch. Does that make sense? So if there is a repeated power, you just keep going. So yeah, like I said, had this been a cubed, we need a plus d over x minus 1 cubed. So just keep it going. But it's not, thankfully, so we'll just stop here. Okay, then we do the same trick. We multiply both sides by x plus 1 times x minus 1 squared. So it cancels out here. And we pick it up there. So then we get 4x is equal to, so this x minus 1 hitting at x minus 1 squared will just give us 1x minus 1 term, right? This is like x squared divided by x. Something divided by itself is just one copy of it. So we'll get 1 x minus 1 out of this, and then the x plus 1 as well. Okay, so we get that. And then this guy, the x minus 1 squared cancels, so we just get x plus 1 here. And then here we get x minus 1 squared. And now I want to play our favorite game. This is really fun to see just these guys annihilating to nothing. So let's let x be equal to 1. So if x is equal to 1, which one of these survives? So if x is 1, we get 4 times 1, which is 4. Now, this 1 minus 1 will go to 0, so that's gone. And this 1 minus 1 will go to 0, so that's gone. So all we're left with is just b times 1 plus 1, which is 2b, which means that b is 2. Okay, so we got that b is 2. Now, let's let x be negative 1. So again, this will go to 0, and this will also go to 0. So now we have that's 0, that's 0. So we just have c times negative 1 minus 1 squared. Oh, sorry, I forgot that. So yeah, 4 times negative 1 is negative 4. That's equal to c times, which means negative 4 is equal to negative 1 minus 1 is negative 2, square is 4. So we get 4c, and this means that c is negative 1. And now you may be thinking, well, we can't do anything to get a. This is like, this sucks. But what we know now is we have some information. So now we're going to use the fact that we know that this is 2 and that this is minus 1. So it just looks like this. And now let's just let x be something very easy so that we don't have to do too much math. Let x be 0. As long as it doesn't kill this, that's all we care about. Because if it kills it, then we can't get a. But it does not. So 4 times 0 is 0. And then we get a times 0 plus 1 times 0 minus 1. Well, this is just 1 times negative 1. So effectively we get negative a. And then we get plus 2 times 0 plus 1, which is just 2. Minus 0 minus 1 squared, which is just going to be 1 when the dust clears. So this is minus 1. And then this 2 minus 1 just gives me a 1. And so now I know immediately if you add a to the left side that a is 1. So beautiful, a is 1. So yeah, the choice of 0 is really nice because it makes life a lot easier. Okay, so now we know A, B, and C. So that's awesome. And that's good because now we know how this thing breaks down. So we now know that this guy actually breaks down into x plus 1 plus, and then we saw that 4x over all this is actually equal to this. So it breaks down into that plus 1 over x minus 1, which is a, plus b, which is 2 over that squared, plus c, or which is a negative 1. Awesome. So that the integral of this is the integral of that. Okay. just make sure I have everything right. Okay, yes I do, okay. And so now, so we can do the ones that we know. This will be 1/2 x squared. This will be plus x. This will be plus the ln of absolute value of x minus 1. Because remember, we'll let u be x minus 1. So then du is just dx. So this is 1 over u. So you get the ln of absolute value of u, but u is that. And then this one similarly will give minus ln of x plus 1. So the only integral that we're a little shaky about is this one. Well, we haven't just seen it yet, I guess. But this one is also a very quick u substitution. Now again, if we let u, sorry I lost my marker, if you let u be x minus 1, du is dx again, and then this integral will just transform to the following. And then that 2 will pull out in front, so this will just be 1 over u squared du. But 1 over u squared is the same as u to the negative 2, which we know how to do this by the power rule. So this becomes, so u to the negative 2 plus 1 over negative 2 plus 1. That's what the power rule would say. So this is just u to the negative 1 over negative 1, aka negative u to the negative 1, which is just negative 1 over u. So this becomes 2 times that, which would just be minus 2 over u. But then what is u? U is x minus 1, so this is 2 all over x minus 1 plus c. And that's it. That's the final answer. That's pretty crazy. And yes, these you can combine these with the log rules, but again, I'm not going to care here. And so we don't have much time left, so maybe let me just show you what I mean by combine these with the log rules. Is remember that ln of x minus, well, the absolute value can be there. Ln of x minus ln y, it doesn't matter if the absolute value is there or not, is the ln of x over y. So the ln of x minus the ln of y, you can write it as a division. So this is equivalent to absolute value now of this one on top, that one on bottom. So that's what I mean by you can rewrite it into something more nice. Okay, awesome. So yeah, we have a few more scenarios and examples to look at, but we'll do that next time. So see you guys then.